We're now ready to summarize these properties of polynomial power functions. These are functions of the form p of x equals x to the n, where n is an integer greater than 1. And we've seen that it all depends on whether the exponent is even or odd. If the exponent is even, the graph looks sort of U-shaped. If the exponent is odd, we have this kind of a shape. And so if n is even, the end behavior is always going to come out this way. As x approaches infinity, the function value approaches infinity. As x approaches minus infinity, the function values approach infinity also. The graph is symmetric about the y-axis if n is even. This is not a one-to-one function because the horizontal line test is not satisfied. And it is an example of an even function. In fact, this is where the name even function comes from, the even powers of x. If n is odd, here's the end behavior. As x approaches infinity, the function values approach infinity. As x approaches minus infinity, the function values approach minus infinity. The graph is symmetric about the origin. So it has origin symmetry. The function is one-to-one, unlike the even powers. And this is a special case of an odd function, and it's where the name odd function comes from. So this is all absolutely essential information to know in this box. And we're going to do a few exercises in just a moment, but I want to make just one more technical point before we do the exercises. Just very briefly, a general power function, so if the word polynomial is not attached to it, it has the form kx to the p where k and p are real numbers. Not all power functions are polynomials. A polynomial is a power function is a polynomial only if the exponent is an integer greater than or equal to 0. So you will see our textbook refer to a function like x to the 1/2 as being a power function, or x to the negative 2 as being a power function. So those are power functions that are not polynomial power functions, and they do not have graphs that match up with the information in the box. So that this box information is only for polynomial power functions, only when the exponent is an integer value greater than 1. All right, let's go ahead and do some exercises now. We're going to do some graph sketching. And in each case, we're going to also state the end behavior for each function. So these graphs, you should be able to just draw. You don't have to label specific points. It's nice to label intercepts when they occur, but other points don't have to be labeled. So for example here, f of x equals x to the 4th. This is a slight transformation, a stretch of the x to the 4th function. So the 0, 0 point will stay the same, and when it gets stretched, it's just still going to have a kind of U shape. So there's a graph. That's all you need to know how to draw. And you need to describe the end behavior. And this is the same as the end behavior of any even polynomial power function. So as x approaches infinity, f of x approaches infinity. As x approaches minus infinity, f of x approaches infinity. And it's unfortunately that we write so much down for just these simple ideas describing that this part of the graph rises, this part of the graph rises, but I do think it's worth you getting comfortable with this notation with the arrows and the infinity symbols. That'll be really helpful for you in calculus. So there's example 1. Okay, example 2. Exercise 2. All right, now I have, again, an even power of x, but the coefficient here is negative 2, and it's really that minus sign that we have to pay attention to. The effect of that minus sign is that we're going to reflect through the x-axis. And when we reflect through the x-axis, the U shape is going to be overturned. And so that's, we haven't seen a graph quite like this, but it's all because of the minus sign. Reflect through x-axis. And so that also affects the end behavior now, because when x approaches infinity, the graph is plunging down. When x approaches minus infinity, the graph is plunging down. So even though this is an even power of x, that minus sign in front of the coefficient affects things, right? As x approaches infinity, f of x approaches minus infinity. As x approaches minus infinity, f of x approaches minus infinity again. So the f of x's both approach minus infinity for this situation. Number 3, I see odd power of x. I'm being stretched by a factor of 10. That's not going to change the basic shape. So it's going to look a lot like the x cubed or x to the 5th. As x approaches infinity, f of x approaches infinity. That's our notation to describe that. As x approaches minus infinity, so as we go that way, f of x approaches minus infinity. So there's our standard end behavior for an odd power. Let's continue. More exercises. Number 4. Okay, minus x to the 5th power. So what I have to really key on is that minus sign in front of the power of x. That's going to reflect through my graph through the x-axis. So I'm going to take the standard shape for an odd power of x, reflect through the x-axis. It's actually going to come down from above, go through 0, 0, do its wiggle, and then keep plunging down. So what does that mean about end behavior? As x approaches infinity here, f of x is approaching minus infinity. As x approaches minus infinity, in this case, f of x approaches infinity, positive infinity, right? Okay. Exercise 5. Now we're getting into slightly more complicated kinds of transformations. I think this is one kind of transformation we encountered in the last chapter, and I just want you to think about how I would think of this. I rearrange the terms. I think of that as minus x to the 5th plus 4. So it's kind of very similar to our example in number 4, but because we have that minus x to the 5th. But then we're also doing a vertical shift upward 4 units. So I'm going to take that shape from the previous exercise, and I'm going to label 4 here on the y-axis so that I can draw this graph coming down and going through its wiggle. And again, let me make that 4 stand out a little better there. Okay. And that's really all we need. You might think about how you could get the x-intercept. I'm not going to talk about that. Well, you should be able to figure out what the x-intercept of that point is. First, let's write down the end behavior. As x approaches infinity, f of x approaches minus infinity. As x approaches minus infinity, f of x approaches infinity, right? Same as the previous example. The x-intercept, if you set the output equal to 0, if you set f of x equal to 0, this is 0 equals 4 minus x to the fifth. X to the fifth equals 4. And so when we solve for x, we have to take the fifth root of 4, which is the same thing as 4 to the 1/5 power. And see if you can get that on a calculator. I get that x is about, I'm going to round this off, 1.32. I round it off. So this is not drawn to, my scales don't match up here. That's officially the fifth root of 4 is that x-intercept. That should be something you can find. If you don't know how to come up with this decimal on your calculator, let me know, and I'll help you with that offline. Okay, number 6. Next example. So here I'm taking 2x cubed, so that's basically the x cubed graph stretched a little bit, and minus 5, I'm shifting down 5. So I'm going to intersect at -5, but no reflecting here, just the standard shape for the x cubed graph, scaled slightly, stretched slightly, and so end behavior as x approaches infinity, f of x approaches infinity, as x approaches minus infinity, f of x approaches minus infinity, right? Same as the end behavior of x cubed. So now here's a point -5 on the y-axis. X-intercept, could we find that point again? Could we set the output equal to 0? 5 equals 2x cubed. 5 halves is x cubed. So the cube root of 5 halves is x. And that's the same thing as 2.5 to the 1/3 power. It's another way to express that same thing. And let me see if I can. 2.5. I got 1.36 when I round off. So the exact value right there is the cube root of 2.5, or 5 halves is the x-intercept. So a little extra calculation there just to label our intercept. Okay, I got a couple more, and I'd like to be able to get through these in this same video segment without getting too long here. Okay, so number 7 is not too bad. We have a 4th power, and so we have our basic U shape, but here we're doing a horizontal shift, right? So we have to shift 3 to the right. Remember, it's counterintuitive with the horizontal shift. So again, I'm just going to label a 3 on my x-axis, and then I just want to draw a U shape that comes down and touches at that point. Now I didn't set up my scales on the y-axis. How can we find the y-intercept here? I'm going to write y-intercept. You're going to set x equal to 0, right? So f of 0, which is 0 minus 3 to the 4th, it's going to be -3 to the 4th, which I think is 81. So that's actually the point 081. Again, it's like I have a very different scale on my y-axis than my x here. The x-intercept is just 3 because that represents the horizontal shift. And now end behavior as x approaches infinity, f of x approaches infinity, as x approaches minus infinity, f of x approaches infinity, because representing the fact that we're rising up at each end. And I think I got just one more of these for us to do together. Number 8. So it's another even power. I'm doing a horizontal shift, in this case to the left 10 units. And because of the minus sign, I have to reflect through the x-axis. So I'm shifting to -10, and I'm reflecting through the x-axis. The effect of the 3 will just be to stretch a bit, which, I don't have to accommodate. Like, it's still the same general shape. And so shift 10 to the left. So we're shifting that way, and also reflect through x-axis. And y-intercept is just going to be set x equal to 0. F of 0 here is -3 times 0 plus -3 times 0 plus 10 to the 6th. That's -3 times 10 to the 6th. That's going to be -3 followed by 6 zeros. That's -3 million. So my scale is changed greatly on the y-axis. So if I'm really fitting that -3 million point on there. And end behavior as x approaches infinity, f of x approaches minus infinity. As x approaches minus infinity, f of x also approaches minus infinity. That's reflecting the fact that both ends of that graph are going downward. And that's it.